Oh hey guys, I didn't see you there. My name is Emma Multani, and today we'll be venturing through the physics of airbags and seatbelts. Although the function seems quite simple, the physics involved in ensuring the safety of the driver and the passenger is more intriguing than you think.
Okay, so in order to understand the physics behind airbags, we have to review some laws that we learned first semester and conceptually understand what is happening and why. So the law of inertia and the Newton's first law is essentially the same thing, that an object at rest will stay at rest and an object in motion will stay in motion with the same speed and the same direction unless acted upon by unbalanced force. And Newton's second law, which can be summarized with the equation force equals mass times acceleration. And Newton's third law, which is for every action, there's an equal or opposite reaction, and also it's showed in the equation F12 is equal to negative F21. Alright, we also need to review something briefly covered first semester, which is impulse. And so basically what impulse is an unbalanced force acting on an object over time, which results in a change in velocity uh, for the object. So basically you would experience impulse. So if you're walking down the hallway and somebody pulls your shirt and you feel like a jerk, you would experience an impulse. Also, we learned a change when you experience an impulse, it is a change in momentum, and so all that is basically changing your velocity. If the force in the impulse is in the same direction as the object, you'll increase momentum, and if the force is in the opposite direction, you will decrease momentum. And by this impulse momentum theorem, we know that the impulse will equal the change in momentum. So we can write this equation, force delta t will equal mass delta velocity, which will come in handy at the end when we calculate just how big of a deal airbags really are. Alright, so basically we need to understand what a collision is in physics, like conceptually. So an object experiences a force for a variable amount of time, which is the collision time, delta t, which results in that object or mass undergoing a change in velocity. And in our example at the end, our velocity final will be 0, and starting will be the speed of the car. Alright, so the main thing airbags do is increase the collision time by compression. So rearranged, we see the formula that force equals m delta v over delta t. As you can see that since it's divided by time, time can create a big difference in the final force um, on the object. So airbags work by extending this time from with the body on your body in the collision. So it will compress to slower or lower the rate of deceleration, ultimately resulting in a lower force. So, and this concept is very common. It's similar to pole vaulting mats and gymnastic mats that when you fall in, the time of your falling is increased, thus reducing the force when you hit the absolute bottom. So seatbelts, which complement airbags, and vice versa, in a collision, when it is sensed by the, collision sensor, the seatbelts will lock, and it will hold you back on your initial jerk. This will hold you back for slightly, so that the airbag can fully deploy, and that it does not deploy in your face, because then that would be a detriment that would not help you in that way. So this is Newton's third law. When it locks and you have the initial jerk, you're putting force into the seatbelt, and it's exerting an equal force on you. So basically how airbags work is there's a collision sensor in the car which is constantly calculating drastic changes in acceleration. And once a drastic change is detected, an airbag sent an electric current through a heating element, and this heating element will ignite a chemical concoction with a catalyst, which rapidly fills the airbag with nitrogen. And from the initial hit of the driver hitting the airbag, it has tiny perforated holes which will start to deflate and increasing the, the collision time. So to put this in perspective, from the time that the collision is detected, it takes roughly 30 to 35 milliseconds to fully deploy an airbag, and the average duration of a human eye blink is 300 milliseconds. So it deploys fairly fast, you could say. So how do airbags help? Well, when your car decelerates and there's a crumple zone at the front, it decelerates very fast, but however, your body is still going the same speed as the car was prior to the collision. So in order to decrease the force of you hitting the steering wheel, it uses compression, or this um, like extended collision time, to lower your deceleration rate of your body, which in turn minimizes the effect of force on your body. And modern day airbag systems, there's also airbags beside you and above you which align your body to the ideal posture for collision. Okay, so here is the calculation for if a car was going 60 miles per hour, and what would be the force applied to your head when your head would hit the steering wheel. So using the same formula that we derived earlier, uh, the force equals delta V over delta T. You can see that our Vf will equal 0 because we will be at rest in the end. Our Vi, which is 26.821, which is the 60 miles per hour. Delta T, this is calculated as directed by the U.S. government, or that you should keep your head roughly 11 to 15 inches from the steering wheel. And going with this velocity with slight deceleration, it would take you roughly 0.009 seconds to reach the steering wheel. And the average mass of a head is 6.5 kilograms. And when we plug this in, we find that the resulting force, if there were no airbags of you hitting the steering wheel, would be roughly 18.5 or 18,500 newtons roughly, uh, which is almost 4,200 pounds. Now, 4,200 pounds, that's a lot of weight. That's almost, well, an elephant is roughly 6,000 pounds, so 2/3 of an elephant on your face. That would be a lot of force. So here's where airbags come in and how big of a deal this compression or the collision time that I've been talking about this whole time. So still the same, velocity final equals 0 and velocity initial 60 miles per hour, which is 26.821 meters per second. Except with airbags now your collision time is roughly 3 seconds, which is a lot longer than it was before. When we plug this in, we find that the force when you hit the steering wheel is roughly 60 newtons, which translates to about 13 pounds. Now, even 13 pounds is significantly less than it was before. The last one was almost 4,000 pounds. This is not including uh, a seatbelt. So a seatbelt reduces your initial jerk. So I guess your velocity initial would be less. So the final force would be even less than it is calculated there.
Wasn't that very interesting? Thank you.